Peter was educated in München, and in years 1994-2001, he studied physics and got a diploma at the Ludwig Maximilians University at München. And for the next 5 years, he studied towards his PhD, which he got in 2005 from the same university, with highest distinction, summa cum laude. Since 2018, Peter is a full professor of physics at the University of Constance. And before, in 2008-2019, he was a research group leader at the Max Planck Institute of Quantum Optics and Ludwig Maximilians University München with Professor Krausch. He did postdoctoral scholar research at Caltech, US, with Professor Sivale, and another postdoctoral research at the University of Vienna, Austria, with Professor Kaufmann. He received many prizes and awards, including in 2022 Falling-Walls Foundation winner in physical sciences. In 2015, he got ERC Consolidator Grant and many other awards. He is publishing in Nature and Science. Peter, the screen is yours.
Yeah, thank you very much for the kind introduction, and especially thank you very much for the great opportunity to speak here. My title is Attosecond and Femtosecond Electron Microscopy. You will see in a minute of what it's actually about. And I ask you to spend something like 10 seconds to contemplate. Look around yourself. What do you see? You see atoms, electrons, molecules. All the materials that you actually are used to is composed of these very simple ingredients. So for me, it's always still astounding that 20 chemical elements and the 1 or 2 electrons, if you count spin, make up all of the complicated materials from computer devices to gases to yourself. Now, physics and chemistry are very good in knowing the structure of molecules, knowing the structure of crystals, knowing the structure of biological specimen. But what is to a large extent still unknown is how these atoms and electrons move around when there is a reaction. Think of a chemical reaction. It doesn't go from initial to final usually. It does some detour. Think of transformation in crystals. Think of computer devices switching. Think of light interacting with some materials. There's a lot of dynamics all the time. And me and my small team have set out, together with colleagues, to develop the experimental techniques to make it visible in space and time, to make movies of atoms and electrons, how they move around when there is reactions taking place in our world. So there's 2 challenges. Atoms are pretty small, picometer distances, and it turns out that the motions are actually really fast. Typically, atomic motions in molecules and condensed matter are femtoseconds. This is determined by the typical binding energies and the typical masses, and it's a very kind of fundamental timescale. 10 or 100 femtoseconds is the fastest possible motion that can happen in any kind of condensed matter at the energy scales that are typical to our surrounding. Now, electronic motion can actually be faster than that, and the relevant scale of time here is the attoseconds, 10 to the minus 18 seconds. An attosecond relates to a second, like a second relates to the age of the universe. Although I work in this field, it's still an incredibly short time. Nevertheless, this is the time scale with which the electrons move around when, for example, light interacts with a molecule or a material and drives them around. So the oscillation period of light is roughly 1 or 2 femtoseconds. So in the sub-cycles, there happens the dynamics. Now, in order to access atomic and electronic motion in space and time, there are various techniques. Lasers can be made into femtosecond pulses quite easily. And recently, we got a Nobel Prize for my colleague Ferenc Krauss and Anne and Paul Augustini for attosecond spectroscopy. They achieved it for the first time that you that they made ultraviolet laser light that is actually so short pulses that you could see attosecond processes. However, the wavelength is still 10 or 20 nanometers, so you're far away of being able to diffract from atoms or to actually see them in real space. Now, the violet blob here, free electron lasers, are a very interesting technology to watch out. However, if you ask a student, how do you see atoms? They should come up with the electron microscope. The electron microscope exists since almost exactly 100 years now, and it's one of the most capable and especially most flexible methods to see tiny things. So nanostructures, molecules, atoms, biological specimen can really be visualized in 20 different ways. However, it is difficult for electrons to become short pulses to make snapshots in time. And this is where we set out. So we take electron microscopy as an available technique and diffraction and combine it with ultra-fast methods to eventually combine the spatial resolution of an electron microscope with the temporal resolution that is offered by laser spectroscopy and attosecond spectroscopy. So that sets the stage, which I will like to explain to you in the following 25 minutes or so. This is a view in our laboratory. To the left, you see our signature instrument. That's an electron microscope. From top to down is the electron beam, and there's a lot of laser optics. To the right, you see me at younger ages at a self-constructed electron microscope, and to the right lower, you see some detailed looks into the optics. It works by the pump-probe principle. You take a very short laser pulse, for example, that is easily available to trigger a reaction, and then you use a very short electron pulse to make an image at just a certain time. And then you repeat this process for different pump-probe delay times, and you get what comes very close to a movie of the dynamics. The biggest challenge is to make the electron pulses short enough. This is how we try to visualize what's actually an electron pulse. The electron has two problems as compared to the photon. First, it's a fermion, so it obeys the Pauli exclusion principle. It cannot be in the same quantum state, many electrons, in contrast to photons, where billions of photons can be put in the same quantum state and make a classical single cycle electric field for femtosecond and attosecond science. This is not possible with electrons. And even worse, the electrons carry a charge, so they repel themselves all the time. And it becomes, the shorter the pulses, the more difficult it becomes to condense these electrons. So this is the so-called space charge problem in electron pulses, and this needs to be solved. Now, our approach is quite radical. We reduce the number of electrons to one. One single electron is not repelling itself, and it can be manipulated as a wave function almost as you like. The experiment now becomes quantum mechanical. You take a pump pulse, trigger your reaction very classically, and you come with this one electron, and you, for example, diffract into a Bragg diffraction pattern. You make one click on the detector. Now you repeat this experiment, pump probe, at the same time delay for roughly 1 million times, and then you get a reasonable image, which is frozen in time by the duration of the electron pulses, and only then you change the pump probe delay and do it again. So you immediately see that we need some high laser repetition rates, and this is part of our research to develop lasers that do it the right thing at the right repetition rate. However, this is technology for us, so I will not report about this in too much detail. Now, how short are these electron pulses if you have only one single electron at a time? This is how they are generated. So you take a femtosecond UV pulse, a short laser pulse, and hit a photocathode, red here. You create photoelectrons, that's Einstein's photoelectric effect, and they are accelerated towards an anode then to form a beam. Now, the photoelectric emission from any imperfect crystal surfaces at a temperature is mostly incoherent. So you start at a lot of initial momenta, that's the black arrows here, that unfortunately also have a distribution of forward components. So during this acceleration, those electrons that already have a forward velocity, they arrive earlier at the target than other ones, and the pulse lengthens in time. So unluckily, the uncertainty principle imposes some very fundamental problem here, which is that the shorter you make these UV pulses, the broader gets this delta P here. of this distribution, because short in time means large in energy. So the shorter you make these emission duration, the longer become your pulses in the end. If you use a very long emission duration, you also have long electron pulses in the end. And that's why there's a fundamental limit where you can't get shorter than that. So this is the second problem we have to fix. And here is our approach. So we take a femtosecond laser and hit an electron source here that produces electron pulses, and they are too long, and we accept that. And now we fight against this dispersion. So we take the cycles of terahertz light, that's a very far infrared waveform that consists of only a single cycle of light, that's the red waveform here, and do something very simple. Electron wave function comes, it's dispersed, the front part is slowed down, and while the electrons pass through this yellow resonator here, the electric field of the optical terahertz radiation flips and accelerates the later part. So the electron then self-compresses to a short duration. Afterwards, there is, of course, some overdispersion. And for characterization, we apply the same principle again, but now the electric field of the terahertz radiation points up and down, and we build a streak camera. So if a long electron pulse comes, the front part is going upwards and the latter part downwards, like here depicted. But if it's short, this will shrink to a point. Now, there is a very funny consequence of this scheme. I am telling you now that these electron pulses here, they can become shorter than any other event in the entire experiment, including the laser. How can this be? So here's a phase-based diagram. To the right, you have time. To the up, you have energy. And we start with an initial photoelectron distribution. That's the red ellipse here, which has something like hundreds of femtoseconds in time. That's a normal commercial femtosecond laser. And it has roughly 1 electron volt in the energy domain. That's the energy bandwidth of the photo emission. And now this pulse disperses during the acceleration to the yellow packet. And now we could, of course, undo this dispersion by slowing it down accordingly. But we can actually decelerate the trailing parts a lot and accelerate the leading parts a lot, such that we do two things simultaneously: reverse the sign of the dispersion from positive, yellow, to negative, blue, but also broaden the spectrum. And now, during the free space propagation, these pulses catch up, and you eventually form a very short pulse in time. Afterwards, there's, of course, some overdispersion. Now, if you do everything right here, and this means we have single electron pulses with no space charge, and all of these transformations are enough linear to not have banana shapes or so, then these green final pulses become as much shorter in time as they have broadened in the energy domain. Now, in contrast to the threefold broadening that is depicted here, we need to consider the actual orders of magnitudes in this concept here. We start with an initial energy bandwidth of 1 electron volt or so at a central energy of, say, 200 kilo electron volts in an electron microscope. So we can not only broaden here by a factor of 3, but 30 or 300 or even 3000, going from the femtoseconds to the attosecond regime. That's the principle here. The second principle, besides of using single electrons with no space charge forces here, in a way, this research here shows that you can use the optical cycles of laser light to imprint their timing onto the wave function of a single electron. Now, this is how we do it in commercial transmission electron microscope. There's a difficulty because it's not easy to get terahertz radiation into that device. So we use this kind of orange waveguide here, but the physics is the same as before, and we can get 19 femtoseconds out of 270 femtoseconds initially. So the 270 femtoseconds is the pulse duration after dispersion, and if we do it right, it shrinks to 19 femtoseconds, which is short enough to see almost any kind of atomic motions that condensed matter physics in chemistry has to offer. Now I bring you a first example before I later tell you how we go to attoseconds. You know the Einstein-de Haas effect. If you have a magnetized material, for example, iron or nickel or something, and you heat it up, then you eventually reach the Curie temperature and you lose this magnetization. At the same time, this angular moment, which is associated with all of the spins, needs to go somewhere else, and it actually goes into a macroscopic rotation of the body. So far, so good. What happens if we demagnetize a material with such a short time that there's simply not enough time for the body to rotate? The angular momentum must be somewhere else. And this has been a question in magnetism for quite some time. It's known that you can demagnetize materials within 300 femtoseconds or so by shining a laser onto them. There's no way that the angular momentum can be taken by any kind of macroscopic rotation. So we set out to answer this question with our electron diffraction. This is the experiment. We take a nickel crystal. So nickel is the material under investigation, which is epitaxially grown on a silicon surface. And we achieve roughly a 30 nanometer thick single nickel crystal here. Now we take so this nickel crystal is actually here then. That's the specimen. We excite this with an excitation laser and demagnetize it. And then we come with short electron pulses that are diffracted and produce an electron diffraction pattern here on the screen. Now, we do this as a function of the initial magnetization and as a function of pump probe time. So we vary two things here. One is the rotation of these two permanent magnets, which actually impose a magnetic field M in the direction either downwards or out of plane here. And then we measure how the diffraction pattern changes as a function of time, in order to see what kind of atomic asymmetry is potentially generated by the magnetic fields. So here's some results. So first left, the diffraction pattern. Electron beam goes into the plane, and you see the expected Bragg spots. Nickel 200 to the right, nickel -200 to the left, nickel 020 upwards, and nickel 0 -20 downwards. So this is these four Bragg spots that are actually interesting for us. And we record now, as a function of time, their intensity. You guys probably know the Debye-Waller effect. So if I heat up this material by a laser pulse and at the same time demagnetize, there is temperature, and these Bragg spots should actually lose their intensity as a function of time. And this is the entirely expected result here. Nothing spectacular here. As a function of time, at 0 comes the laser. You see that all of these Bragg spots, the 200, but also the 220 here outside, they lose quite some substantial intensity of a few percent within 1 or 2 picosecond times. This is actually a very expected result, because the laser initially only heats up the electrons in this metal, and then it takes for the hot electron gas to couple to the phonons roughly 1 or 2 picoseconds. Now, the surprising result is the lower panel, and we plot here the intensity of the 200 and -200 spot averaged, divided by those spots upper and lower, right? So left and right are averaged and divided by upper and lower. And nickel is a cubic crystal, and if you have the equipartition theorem, then any kind of temperature that you have should affect all of these Bragg spots in exactly the same way, so we expect no change. Everything should stay at 1. However, we see clearly here that after time 0, you create an anisotropy. The left-right Bragg spot actually become more intense as a function of time than their counterparts up-down for horizontal magnetization. That's the blue trace here. But for a vertical initial magnetization of the entire material, you have the opposite effect. So this first means that the magnetization of the material actually has something to do with the atomic motions. So there's a direct spin-phonon coupling, which is not very much considered so far in magnetism. But second, we violate the equipartition theory. If you look at later times, you have the left-right Bragg spot at a different temperature, if you want so, than the upper-lower, and opposite. And it turns out that the underlying physics behind this is what we call the atomic Einstein-de Haas effect. If the initial magnetization points upwards and we demagnetize, this angular momentum, every single atom has now a spin which is originally aligned upwards, but after the magnetization, it's random. So it loses a certain angular momentum from the spin system, and this spin system arrives at a rotational motion of the atom itself around its equilibrium position. These oscillations are circles. And in the case of an upward magnetization, the electron beam appears to see disorder in this direction, but not any disorder in the other one, or not any additional one. And that's why the left-right bragg spot here becomes weaker than these two here, right? The situation changes if the initial magnetization is sideways, then these oscillations are this way, and we see a disorder here, but not here. And it all fits. So by the way, the oscillation amplitude is 2 picometers here. So from these results, we conclude that the Einstein-de Haas effect, where a magnetized material causes a macroscopic rotation of the body, needs to be amended in certain cases by an intermediate step where the atoms themselves start to rotate, and then it takes roughly nanoseconds for the entire material to rotate. So this is one example where we can use our terahertz compressed electron pulses, now not in microscopy, but in diffraction, to actually learn something about atomic motions in a complicated material. Now I promised you attoseconds. So the experiment is actually very similar, but on different scales. So we again take an electron beam up to down, and now we don't use single-cycle terahertz fields to compress the electrons, but we use near-infrared laser light at 1 micrometer wavelength. That's the red one. The physics, however, is the same. Electrons are decelerated, accelerated, decelerated, accelerated in very quick sequence, and we create a sequence or train of attosecond pulses here. It turns out that they are locked to a second laser beam and can be characterized in this way. Now, at such fast time scales, the electron is no longer a point particle, but it's actually a wave function. So this experiment becomes quantum mechanical. Here, I tried to explain what happens with this diagram here. So you see in blue here an electron wave packet as a function of time, so that's psi squared. And it turns out that this covers 2 or 3 optical cycles of the laser, which imprints a phase, so a time-dependent acceleration. This is the same like in radio, where you have a megahertz carrier or so that is modulated by a kilohertz sound wave into narrower or wider oscillations. The same happens here, that the petahertz frequency of the light, red, modulates their 10 to the 20 or so de Broglie frequency of the electron de Broglie wave. Now, if you fully transform this to the energy, you get coherent sidebands. These are expected, and I will show you in a second that they actually appear. Now, what happens if the incoming, this is what happens here. What happens if we do the same with an already compressed attosecond electron pulse train here? If we, in the middle panel here, you see that in principle, classically, all of these electrons would be accelerated, and in the lower one, all of them would be decelerated. Quantum mechanically, there happens what's sketched here to the right. So the envelope goes to the right or to the left. That's correct. But in reality, the sidebands simply increase or decrease here. So you see that this sideband increases and this one decreases, or this one increases and this one decreases. And this is the experiment where you see still washed out at that time. So this is already 3 years ago, that you either have this sideband here, or this, or this, or this, in an almost alternating way. And simulation and experiment are a very nice agreement. So you see here that we actually create these attosecond electron pulses like depicted here. By the way, this is a detour. So the main purpose of our research is to see atoms and electrons in space and time. But we are also doing some quantum mechanics. It turns out that this if this can actually be made 0 and this 1, or this 0 and this 1, then we actually have almost the properties of a qubit. So if you are more interested in that topic, then you should read this publication here. It's not very perfect, but it has some nice correspondences, and we can make the free electron into a qubit. So far, it's only 1. If we create 2 or 3 electrons and somehow couple them, then we can think about quantum operations with the free electron as an elementary particle. Now, but back to the main story here. This is what we do in the experiment now with attosecond time resolution. Here is again the generation of our pulses, so periodic acceleration and deceleration. And now we use the laser cycles to hit a specimen and try to record the optical response, so to see the cycles of light in space and time. This is a detailed view of the specimen here in this experiment. So this is a nanoresonator here, and we come from a slightly 45 and 45 three-dimensional direction with a laser beam, and we create surface plasmon polaritons. That's the light blue and orange fields here that my student tried to depict, that oscillate here as a function of space and time and make a nanoplasmonic functionality here. Now, at the same time as the excitation cycles come the electron pulses, and they are now short enough to see time-frozen electric fields. So this pulse duration here is short enough that while these electron passes through, there's actually not much dynamics here. So the electron is either accelerated, the electron wave function, or decelerated as a function of position and time. And now, how do we detect this in the experiment? We have here this very nice device, which is an energy analyzer here, which we can filter away only those ones. So we throw away all of these electrons that have not gained or lost energy, and we only look at those that have gained and produce energy filtered images. And now finally, here is the result. So what you see here in white and in black is the addition or subtraction of kinetic energy of the attosecond electron pulses in the cycles of light as they propagate on nanometer dimensions along this needle. So we have here a first experiment where nanometer resolution of an electron microscope is combined with attosecond resolution in time. And you see here that the surface wave moves along the tip towards the shaft. If you want, so this is a time-lapse movie with a magnification of 10 to the 17 roughly. So 10 to the 17 times slower than in reality. But this is the cycles of light moving around. So we can do some more experiments and actually use circular polarization to excite now these plasmons and see what happens. And these are the results. So you see on the left panel for left circular excitation and for the right for right circular. And there is several interesting things happen. First of all, you see that these fringes on the upper side here are denser than on the lower side. So the phase velocity is roughly the speed of light on the upper left side of these antenna, these nanoneedles, and it's roughly 1.4 times the speed of light on the lower right side. Don't worry, this is a phase velocity, so nothing is violated here. What happens on the lower side comes the laser here, and it's of course reflected. At the same time, you have the surface plasma and polariton propagating along here, and all of these three things interfere and produce this slightly superluminal velocity. However, on this side, you simply see the surface plasma and polariton propagate here at roughly the speed of light, which is the surface plasma and polariton wavelength in tungsten. Tungsten is our material. There's one more thing that you can see here, which is somehow it's weaker here and stronger here and weaker here. So it depends on the chirality of the excitation laser, and this is the explanation. Look first at the big image here, the artistic image. You create, when you do circular excitation, you create a circular moving plasma polariton, and blue here means accelerating electric fields, and red means decelerating electric fields. So these point upwards, and these point this direction. And now the electrons that pass left or right can either surf or anti-surf on this wave. If you look here, you see that electrons that pass to the right of this tip see the swirl going with them, and this is like a surfer on a wave, while the electrons on this side here, they go against this wave. So they are shorter, effectively shorter in the wave than those which are effectively longer in this wave. So this means you see more on the one side for the one circular polarization and less for the other one. So you see here that our method can not only see the cycles of light in terms of their fields, but also their chirality. Some more examples before I come to the end. This is an inverse nanostructure. Everything is a thin silicon membrane here, but in the middle there is a slit built into it. So that's a piece of vacuum here, which is roughly 1 micrometer long and 80 nanometers thick. And now you see that this is an inverse antenna, if you want so. You see indeed that there is a dipole mode and a quadrupole mode. So you see probably an oscillation like this, and you see also an oscillation like this and like this. Yeah. So there's a quadrupole and a dipole mode. And then you see that this nano antenna, like a radio antenna in TV, can actually re-radiate. And it does so in form of the dipole radiation. The quadrupole cannot re-radiate, but the dipole can. And you see here these optical cycles going this way with their typical curvature, and their a phase velocity that is actually a little larger than the speed of light in silicon, because part of the mode is above and below the surface. So the silicon substrate is 200 nanometers, and the wavelength, the frequency is the frequency of 1,000 nanometer light. So there's evanescent waves. And here is my final example for today. This is an arrangement of 4 such slits. Such arrangements are important for technology because researchers are trying to build metamaterials, which is dedicated nanostructures that modulate light in a way that nature cannot do. For example, to create cloaking devices or negative refractive index or chiral sensors or such things. And what we do here is a very first step into that direction. Simply have 4 of these antennae in special geometries and see what kind of field in space and time is actually generated. And you see here their response in on the most fundamental quantity that optics and electrodynamics has to offer. That's the electric fields in space and time. So with that, let me conclude. Single electron pulses under light cycle control are the 2 technological ideas that have enabled everything that you saw. The single electron is not repelling itself, and the cycles of light are used to imprint the necessary timing onto the electron beam, which itself offers the necessary spatial resolution in microscopy or diffraction. I showed you 2 examples how we can see atoms and electrons in space and time. One thing that is important for me is that both the laser and the electron microscope are very versatile devices. So if the scientific question is important enough, we can surely adapt an electron microscope and a laser to match the properties of this material and help to understand as a function of space and time. Thank you very much for your attention.
Thank you. Now we have a time for questions. But before any appears, let me ask my questions. So you showed us one example of diffraction for very simple material. And it was diffraction collected for one particular orientation of that material, right? Very thin sample of material.
So the material is 20 nanometer, 30 nanometer of nickel single crystal on a 20 nanometer silicon substrate.
Within your setup, is it possible to rotate it and to collect 3-dimensional diffraction image? Like the full...
Yes, for this experiment has not been required. So we intentionally chose this geometry here to be maximum sensitive to the rotational phonons that we searched for.
I'm thinking about really seeing details of more, or let's say less symmetric systems having more atoms, and then it would require to collect much more reflection intensity.
Sure, this is not a problem at all. The only problem here is that we use these single electrons at a time that are laser generated. So you have roughly, you have not as much electron beam current than in non-pulsed experiments. Let me phrase it this way. So the number of electrons per second is lower. But in principle, you can see very higher order diffractions in the same way as we do it in normal electron crystallography.
So basically, you can see how atoms are moving. I mean, describe the movement of atoms in the crystal. Let's say, would it be possible to observe it for molecular crystals, for example?
The short answer is yes. The longer answer is in this experiment, we looked, it turned out that these atomic rotations have random phase. So look, if you look at my attempt to picture it, they have all random phase. So it's a sub-temperature in this rotational domain that we see by the Deber-Waller effect. So if these atoms would all do the same coherently, then we would see a left-right Bragg spot, you would see an oscillation of the Bragg spots as a function of time. This happens not here, but this does in no way preclude that we would be able to see something if something like this would happen. So therefore, my answer, yes. If you give us a molecular crystal that does a deterministic chemical reaction, then we would be able to see it, as far as the resolution of diffraction in this kind of experiment allows.
And what's the limitation for the resolution and the technical limitation of this?
Yeah, the brightness of the electron source is roughly 1,000 or 10,000 times lower than in a typical electron diffraction experiment, but we trade this for femtosecond resolution and time. So practically, practically you see this diffraction pattern we are kind of proud of, but it has been obtained with femtosecond single electron pulses. So it's not super easy to obtain it. And you see here from the data that we can roughly see intensity changes of 10 to minus 3 at a certain noise here after a total averaging of 30 hours or so. So this is roughly the signal to noise in the intensities that we currently have. So of course, going to femtoseconds comes at the cost of reduced signal to noise. But you get the femtosecond information in time.
What kind of detectors you are using?
This experiment has been done with a phosphor screen on a CCD camera. In our more modern electron microscope, we have a single electron counting detector. It's a Timepics camera.
My dream would be to collect enough diffraction spots to do the back Fourier transform to see experimental distribution of electrostatic potential in the sample and how it changes with time.
This is in principle possible. You suffer from Friedel's principle, of course. So you need to solve the phase problem, and second, you need to average for long enough to get good enough data. But in principle, it's possible.
So that what doesn't mean long enough? Several days or just hours?
Yeah. So as I told you, this experiment has been done in roughly 30 hours of averaging at roughly 10 to minus 3 level of changes that we can see. Of course, it's possible to improve this. The way to improve it is to actually change the repetition rate of this experiment here. Here is the basic experiment. The limit is, or let's go to this setup here. The real fundamental limit is that after the excitation pulse here, you need to give the specimen enough time to relax back before the next pump pulse comes, right? This determines the maximum rate of which these electron pulses can come. And in our experiment, it is something like 2 megahertz. So we come with one single electron every 50 microseconds. and this determines the average amount of information that you get here.
Yeah, okay.
Ideally, if you have a specimen that reacts forward and backward in a quicker time and gets rid of the heat, then this can be improved. This will probably be, these are the technical limitations that actually seem to be, from a technological perspective, quite fundamental. From a physical perspective, it's only a matter of source brightness.
I guess you measure many kinds of materials. Do you have examples in which you obtain data which you cannot really explain by quantum chemical calculations, or the level of calculations? Or that's not the question.
This example qualifies. So
Yeah.
I'm very sure that the magnetic guys cannot simulate the femtosecond onset of a rotation on atomic dimensions yet. So at least we found prior to our publication no attempt to do so. Because spin-phonon coupling is a very difficult thing in quantum chemistry in the condensed phase, because no one actually knows the forces. If you change a spin, there must be some forces on the underlying atom, but this is actually something complicated. So I would say this experiment is one where we actually made a discovery. Okay, thank you very much for the opportunity to present.